In this video, we're going to try to understand transmission lines by making circuit models for wires. We need to do this because we don't have a great model of what a transmission line does right now. Since we don't have a mathematical model of a transmission line, it could conceivably turn the signal on the left into any of the signals on the right. All of them have some delay, but we don't know which of them is right. We don't have many clues yet, so we're going to start by making circuit models of wires to try to solve. It's easiest to make circuit models of wires if you start with a few basic facts. First, wires are made of metal, so they have some resistance. We expect to see a resistance in series between the signal connectors at either end of a transmission line. Second, transmission lines always have both a conductor and a return path. That means they're made of two pieces of metal that are usually close together. Charge building up on pieces of metal that are close together makes a capacitance. So there's a capacitor between the conductor and the return path in a wire. Because our return path is grounded, that capacitance will have to be hooked from the signal to ground, which we call being in shunt. The simplest circuit model we could imagine that matches our basic facts is a lumped RC model. In this model, we just replace the wire with a series resistor, and we put a shunt cap on one side or the other of the wire. This model does make a delay. Sine waves driven in this wire would have a phase shift, which means that their zero crossings would come later, and square waves would have a rise time, which overall shifts signals to the right. However, the model has a few problems. We're going to focus on one, which is that it's pessimistic. This model imagines all of the capacitance in the wire comes after all of the resistance in the wire, when they're actually smeared together along the length. When we treat all of the capacitance or resistance of an element as happening at one place, we call it a lumped model. So in this case we have a lumped capacitance at the end of our transmission line. And for the record, all of the circuits you've seen in your life so far have used lumped models. We can try to make lumped models work for us a little bit better by making something called a T or a pi model. In T models, the capacitance is put in the middle of the resistance. So we split the lumped resistance of the wire into two lumped resistances of R wire over 2 and put the capacitor in shunt between them. In pi models, instead, we cut the capacitance in half. We put half of our lumped capacitance on the left side of our wire and half of the lumped capacitance on the right side of our wire. These models actually do a really good job of predicting delays for digital designs, and they're good for hand analysis, so they're popular and useful tools to have in your back pocket. However, they're still not perfectly accurate. So you might try to increase your accuracy, for instance, by making a two-segment T model, where we imagine we had 4 segments of R wire over 4 and 2 capacitors of C wire over 2, and then we stick those two T segments back to back. Or instead, you could go to a 3-segment or a 4-segment model, and eventually, when you cut up the wire into an infinite number of segments, each of which is differentially small, you wind up with something called a distributed model, which describes the voltage and the current in a wire using differential equations. We use differential models for RF design, and in particular we use something called a differential RLGC model. The differential RLGC model has a few more circuit elements than the T or the pi model. Each differential element is comprised of a tiny resistor, a tiny inductor, a tiny capacitance in shunt, and a tiny conductance in shunt. We use lowercase letters in this differential model because each of them represents a value per unit length. ds is the differential length of the wire, so the resistance in this element is the resistance per unit length times a differential length. Now, we've added these two elements, inductance and conductance. We need to include inductance because return currents and forward currents both create magnetic fields, and fields coupled between inductors is how you create an inductor. As an example, consider a wire on a PCB on the top copper layer that's running over a ground plane on the bottom copper. If you apply the right-hand rule to the current directions in these wires, you'll see that both of them create magnetic fields that point into the page in between them, which is an example of creating an inductor. That's coupling flux between conductors. The conductance is easier to explain. The materials that you use to make dielectrics between the center pins and ground shields of transmission lines aren't always perfect. Sometimes they leak a little bit of current. It's usually pretty small. So, in summary, lumped models sum many small circuit elements into a big one and put it in one place in your circuit. Distributed models instead cut a circuit into tiny differential pieces and end up with a differential equation. And we use differential RLGC models in order to build up transmission lines. And just as an aside, you can get away with lumped RC, T, or Pi models for digital design.